There we go. Maybe I can make this. Okay, now you can also hear my voice. Mm-hmm. And then we can select V and V. Perfect. So let's start writing the code. Um, mhm, 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 mhm. So first, let's write some dummy code, which I'm not going to use right now. So we have import OS from Torch Vision, import the datasets transforms form. So what I'm doing right now is I'm following this guide on Pytorch going modular. And I'm going to basically like copy all of this and understand how he is basically converting his code, his Jupyter code into multiple different files, so multiple smaller files. And then I will use a similar approach to then write a code for Alexnet and then convert it also as modular for myself. So that is the goal. So from so he is importing the datasets and the transforms. Um, And then what he's doing is he does from torch.utils. I think this is like too small for you guys. So maybe let's make it a bit bigger so you guys can see what I'm doing. So from torch utils, utils.data, I am importing data loader. Another thing, I don't have Pytorch in this virtual environment. So Pytorch install GPU. So you can go on Google and you can search for PyTorch install Google. And then over here, you go to get started. And then you can copy this entire link, go back. So I'm using WSL, which means I'm running Linux right now. And I'm not going to use Windows, I'm going to use Linux. And just copy this entire thing. And then I can open my terminal, and in my terminal I can write pip, or I can just paste this thing and it will install Pytorch. In the meanwhile, while it's installing Pytorch, I can start with writing the code. So data loader, then we can say, hey, the number of workers that we are going to have. So this is going to help us when we're basically running our code in parallel. This is going to be os dot CPU underscore count. That will give you how many number of workers we have. Then we can define a function called create data loaders. And what this will do is it will help us to create the data loaders. So we can say this is going to be our training directory. We're going to have a test directory, which is also going to be a string. We're going to have a transform. This is going to be transforms.compose. So right now my IntelliSense is not working because I'm still installing PyTorch right now in the background, but once it gets installed, then I will get my IntelliSense as well. So this will basically help us for data augmentation. The directories is where our images and our labels or whatever our data set is in. Then we can also specify our batch size. So basically over here, we're just giving arguments to our function called create data loaders, which we can then reuse again and again. So we are saying that our training directory, test directory, these are of data type string. The transform is of data type transform.compose, and batch size is of type integer. And we're also going to define one more parameter, which is going to be the number of workers. So this is going to be, again, an integer of number of workers, which we have defined over here. Perfect. So that's our function. Now I'm just going to copy paste this entire thing, which I've just explained right now. And it's always really nice to have talk strings explaining what the function is doing. So this takes in the training directory, the testing directory paths, and turns them into PyTorch datasets and then into PyTorch data loaders. Again, just explaining what the training directory is, what the test directory is. Transform is for the data augmentation. Batch size is for the number of samples that you're going to put in each of the data loaders, and number of workers is the number of workers per data loader. And then you are also defining what your return is going to be. So you're basically giving an example that, hey, I will use this in this way. Like, this is how you're going to basically be using this. Okay, so um, let's continue. So the first thing that we are going to do is we're going to say use image folder to create data sets, possibly data sets, plural. Brother, what is Alexnet? Good question. Alexnet is basically like a deep learning model which is used for computer vision tasks. It was one of the very first computer vision model, which was an AI model used for images and for videos. So yeah, this came out in like 2012, and I'm just trying to implement this. I hope that answers your question, Walid Gul 2157. If I, it's an LM, right? Oh, what do you mean by LM? I don't know. What's LM? LLM. No, 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 no. It's not an LLM. It's not an LLM. Yeah. It's it it uses a neural network. An LLM, but you are saying AI. Yeah, AI equals to LLM. No, so the thing is that not all AI is LLM. Um, like, I think I was also showing this to someone else the other day. Uh, I have this I have this German version of it, but like KI, or you can think of it as AI, and then you have machine learning, and then you have deep learning, and then you have an LLM inside there. Good work, continue. Thank you so much, Walid. By the way, where are you from? I don't know, where are you from? Um, I mean, if you don't want to say, it's perfectly fine. But yeah. Okay, back to implementation. Train. I am everywhere. Okay. 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 Um, all right. That's the funny way of saying that you don't want to tell me where you're from. Uh, okay, let's drink a little bit. So, um, we have um so basically we have our, just a second. Yes. So we have our image folder. This is basically a sub function for our datasets function given by Pytorch, and what it does is it helps us to quickly create a data loader, um, or not the data loader, but convert your images into tensors, which can uh, then can be used. So just a second. So we can take a look at this a little bit. Yeah, I'm just waiting for PyTorch to get installed, and then I can start working with it. It usually takes a little bit of time installing it for the first time, but once it gets installed, then it's very easy to use. Da, 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 do. Do, 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 do. I think I'm gonna make this a little bit bigger. Mhm, mhm. Do, 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 do. Do, do, do. Do, 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 do. Mm, 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 mm. Still waiting on the library to get installed. Okay, so yes, finally. So I also need to get the code for PyTorch GPU. There we go. Okay. Installing. Let's just run it over here. So I will do import torch. Think so it worked. Torch dot CUDA. Yeah, there we go. Torch dot CUDA dot CUDA dot is available, and it says true, so it is reading our CUDA. And then we can also write torch dot underscore version underscore, and it says that we're using 2.10.0 with CU 126. And then we can also write torch vision dot underscore version da, 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 and torch vision is not defined, so I think we have to install torch vision. Okay, Jupyter Notebook is also set up. Da, 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 da. Please work. Please work. Why does it not work? Tell me one thing, nothing but a heartache. Tell me one thing, nothing but a heartache. Tell me why I'm never gonna hear you say. Just waiting, waiting, waiting. Maybe I'm going to restart VS Code. VS Code. Da 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 da. Please work. Yes, finally it works. Come on, man, it doesn't take that long. Why? I think maybe it's like caching or something. I do not know why it's taking so long to run. Usually this runs pretty fast. But maybe... okay. Time to install libraries. So pip install matplotlib. You may have installed Python packages in your Python global. No, I did not. I did not do it in the global version. Now we wait, now we wait, now we wait, and rerun this thing. Zupa. So we have our Python version, we have our Torch Vision version, and now I do not know what this percentage is. So this is downloading the dataset, but I don't know why. Maybe because I didn't have TQDM. Maybe that's why I didn't get the entire like progress bar when I was installing it. Let me take a look at the requirements.txt file if they have provided or not. No. Oh yeah, sorry. Pip install tqdum. Okay. All right. So what I basically did was I just downloaded a dummy fashion MNIST dataset. I saved this in a root data folder. So this is where all of the images are. And I'm basically the images, they usually come in the PIL format. So PIL stands for, what does PIL stands for? I think it's like uh, Python image library. But usually we want to convert that into tensors, and basically whatever operation we're going to do is going to be in tensors. That's why we are converting that into tensors, and then we can transform the label as well. So let's take a look. This is how it would look like, right? So these are like tensor values. And then we can also look at its shape. So the shape is 12828. And what that basically means is the first index is telling you the channel. So we are working with gray and white, the grayscale, black and white images, and the dimension of the image is 28 by 28. Then we can also run this. Not for this, but only for this. And it will tell you that how many samples do we have or how many images do we have. And for now, we have like 6,000 images, and we have 6,000 labels. And over here, we are outputting our image and also the label for the first image. So train data sample 0. So this entire image is for the class 9, which I forgot what it was in the fashion MNIST dataset. And then we can also visualize what it looks like. So this is an image of a boot with the class 9. And then we can also view other images as well, and we can give proper names to this by using the class name function. So we can save that over, where should we save? We shall save it here. And then when we run this, we shall see that we have all of the classes, and then we can also see them in grayscale, which is pretty cool. Good, 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 good. So let's start by a quick revision. And the idea is that we are basically going to take our fashion MNIST dataset, we're going to pass it through our data loader so that we have a batch. So we have like batches, which is basically calculated by number of samples. So we have 6,000 samples divided by 32. That will basically tell you how many batches do we have, or you can imagine them as like packages of images. And for each package or for each batch, we are going to have 32 images or samples. So that's what we're going to do with the data. Sorry, excuse me, with the data loader. So let's write our data loader. And the data loader is going to be from torch.utils.data import the data loader. We're going to keep our batch size as 32. We're going to say train data loader equals to data loader, and then train data, comma, let's do it, and yeah, train data. So how we are basically converting our data set into an iteratable so that we can iterate over it. And sometimes when you don't know what parameters to enter, you can always hover over it, or I think it's like shift enter or something. Shift enter. No. Yeah, I think it's shift enter on Google Colab. I don't know what's the command for on VS Code, but you can hover over it and then you can look at the docs string. So it gives you like what is the arguments and like what everything means, right? So what we are interested right now is the data, the train data. We are interested in setting the batch size to the batch size that we have defined earlier. And then we are going to say that shuffle equals to true. That's basically it. And to see what we have created, we can then do print or printf, whoops, and then we can say data loaders, and then we can say train data loader. So we're going to print that, and then we can also see the length as well. So the length is going to be length of data train data loader, and then we can do this as the length of the training data loader. Um, we can also see the batches as well, but that's just going to be 32. So we have this batches of batch size, and we are going to this and this. So we have an object of data loader of torch.utils.dataloader.dataloader, and we're basically saying that we have 1,875 batches of 32 images, which is pretty nice. If we want to get an image from our data loader, then in that particular case, what we can do is we can first define a seed, because when we're picking an element from our data loader, and if we're randomly picking it, and if we want to make sure that we want to have reproducible results, then we have to set a seed. So we're going to say that the manual seed is going to be 42. And for a random index, we're going to have torch.random integer from 0 to the length of the training length of the training feature batch size, which I haven't defined yet. So let's define that. So the training features batch and the training labels batch, that is the next iter of the train data loader. Why? Because data loader itself is an iteratable. And we are basically grabbing an image, or we're iterating through it, and we're grabbing that for an image, what is going to be the shape. So the features batch dot shape, and what is going to be the shape of the label. So the labels dot batch dot shape. So for an image, 32 is basically the batch size, 1 is basically grayscale, and then 28 by 28 is the image, and then we're basically saying that we have 32 labels. So this is what we have. We have 32 samples in one batch, and the height and the width of the image is basically 32 by 32, and 1 is basically donating that you have number of channels as black and white. Okay. Okay, so that is basically telling you what is inside the data loader. Now to basically visualize it, we're basically going to get the train features batch. That's our so we're grabbing a random index from 0 to 32, and then we keep the size as 1. Um, and size is basically saying over here, which is a tuple defining the shape of the output tensor. Okay. And then we write dot item. And now if you write the random index, we will always get 6 because we have set the manual speed to 42. Okay. So the data loader is iteratable. This means that it knows how to go through your data, but it doesn't hold the position itself. It's like a book. It has all of the pages, but it doesn't have any bookmark by default. Iter, train, data loader, this creates a bookmark, and iterator initializes the state, prepares the workers if you're working with numbers that's greater than 0. Okay, next iter, this iterator to actually turn the page. Uh, you might wonder, why can't we just do train data loader 0? There are 3 main reasons. A dataset might have 1 million images. If the data loader acted like a list, it would try to load everything into the RAM at once. By using an iterator, Pytorch only loads the current batch into the memory. Okay, so the reason why we're using it as an iterator is because if it was a list, then it would load everything into the memory. So that's not good. Shuffling equals to true, so you always get some first item as something else. And then you can also do multi-processing, so data loader often uses multiple CPU cores to prefetch the data. The iter calls up these background processes so that when you call the next, the data is already waiting for you. Okay, that's good to know. Next is this function. Let's understand this. So 0 to 32. Okay, so if we don't use an item, it will return a tensor object like this. But if we write item, then that basically helps us to grab like this integer number. Okay, that's good. Let's get back. Then for this random index that we just calculated, then we can grab an image and a label from our data loader. So this will be train features batch. So um, for this random batch, we are basically going to grab its random index and then train features, no, sorry, train labels batch, the random index. And then we can also see this. So we can write plot dot I'm show image dot squeeze, and then cmap equals to gray, and as the title we're going to write class names, and the class name is going to be the label, and plot dot axis off, so we don't want to see the We don't want these numbers, the x-axis and the y-axis numbers. And then we can write print the shape if you want. So I'm just going to grab it over here. And that gives you an image of from our from this batch, which is pretty good. Okay. So before I'm going to now continue, we have a rough understanding of um, the data loader part. Let's take a look at chat. Nothing in the chat. That's good. So let's move forward. Okay. So since we already had datasets.fashion mnist dataset, and this was in the form of tensors, which could be used by Pytorch. If we had custom dataset, then in that case, we would go for this approach, which is we give our directory, that this is the training directory, this is the test directory, and then we are basically using this image folder to, I think, convert it into a format which then be used by the data loader. Okay, so the image folder is a dataset class. Its only job is to organize and label your files on your hard drive. So data, train, cats, image, this. Image folder automatically realizes that the cats is class 0 and the dogs is class 1. It handles the file paths, mapping the folder names to integer labels, and applies the transforms. Data loader, on the other hand, is then adding like a wrapper on the top of the dataset. Okay, perfect. We'll move on then. So for our use case, yeah, I'll still write this function and then we'll decide what we're going to do later on. Okay, let's go back to the modular page. There we go. Okay, so we have our training directory over here, and then we're going to set our transform to the transform that we have defined earlier. Similarly for the test directory, so this is going to be the datasets.the_image folder, test directory, and the image, transform equals to the transform. Then we are basically going to get our class names. So the class names are going to be the train data dot classes. And then we are going to convert the images into data loaders. So this is get class names, and then this is going to be turn the images into data loaders. So we're going to write train data loader equals to the data loader, where we have our training data, we have our batch size as our batch size in the function that we defined. We're going to have shuffle equals to true. So we want to shuffle the images as well. We want to keep the number of workers equals to the number of workers that we've defined earlier, and pin memory equals to true. Now, if I remember correctly, you use pin equals to memory, and what it does is the data loader will copy the tensors into the device CUDA pinned memory before returning them. If your data elements are a custom type or collate fn returns a batch type that is a custom type, see the example below. I remember that what it does is it keeps your data into the memory, and this helps in like faster training times. But let me still read it in the official Pytorch documentation in memory. If you load your samples in a dataset on CPU and you would like to push it during training to the GPU, you can speed up the host to device transfer by enabling pin_memory. This lets your data loader allocate the samples in page locked memory, which speeds up the transfer. So yeah, so it's basically like remembering, I think, that you want to keep this in memory, so it um, loads your data um, from CPU to GPU. So that's pretty useful. Um, okay, similarly like this, we're then going to convert, we're also going to create a test data loader as well. So this will be test data loader. So over here, we'll just have the test data. Why do I not have my test data? Because I have a training directory, a test directory. Oh, because I didn't make a, yeah, okay. It doesn't matter. And then at the very end, we're going to return our train data loader and our test data loader. So this function helps us to do what thing? This whole thing. So we just give our directories that, hey, this is where our images are at. This is where my training data is at. This is where my testing data is at. And then it will help me to um, create data loaders for it. So this is for my custom data loader, which is pretty good. And so we have step 1, which is creating data loaders for our data set. That's the first step. And if we want to create our data loader, then this is how we're going to create our data loader. Then the second step is the model. So step 2, create the model. So let's create it. So the model is going to be something very simple. We'll just say import torch, from torch import nn, and then we're going to have class tiny VGG network with nn.module inheriting that and defining an init, and then we have the self, we have an input shape of the image which is going to be an integer. We're going to define how many hidden units that we're going to have. Hidden units, this is going to be an integer. We're going to have an output shape, what we're expecting the output to be, and then we expect it to give us nothing, so it's a void function. Then we do self super dot init. So we are first initializing nn.module first, and then this gets initialized. So self dot, now we're defining our convolution block. So the first convolution is going to be an nn.sequential. This is going to be an nn.conv2d. Not what I had in plan, but where was that? Yeah, we're going to have a convolution 2D with the in channels as input shape. We're going to have the out channels. So let me, before I do this, let me add the doc string. Replicates the tiny VGG architecture from the CNN explainer website in the this input shape, and integer indicating the number of input channels, hidden units, and integer indicating the number of hidden units between the layers, and output shape is defining indicating the number of output units. So output channels is going to be the hidden units, and then the kernel size will be 3, and then the stride will be 1, and the padding will be 0. Then we are going to have nn.relu. Then we're going to have another convolution 2D with the in channels as the hidden units, the out channels as again the hidden units, and then we're going to have the kernel size as 3, the stride as the stride as 1, and then we're going to have padding as 0. Then for the next layer, we're going to have our first activation function. After the activation function, we're going to have max pooling 2D of kernel size 2, our stride also as 2, and then we're going to create our second convolution block. So this was our first convolution block. Now we're going to do it again. Self.convolution block 2. This is going to be nn.sequential, nn.conv2d. In channels is going to be 1 from the previous one, so hidden units. Out channels is going to be hidden units. You can write that again and again, like in channels, out channels, but if you get what it is, you can just skip this, and then you can just define this as kernel size as 3 and your padding as 0. nn.conv, sorry, nn.relu, always apply your activation function. After that, then you have nn.conv2d, you have your hidden units, your kernel size is 3, your padding equals to 0. Okay, nothing in the chat so far, so that's okay. Okay. Then we have our what? So convolution layer, the activation function, then another convolution layer. So we did this, then we copy this again, and L should be capital. We want our green stuff. Then we do max pooling of 2, which is basically exactly this thing. And once we are done with 2 convolution blocks, then we are going to set our classifier, which is the last layer. So this is self.classifier, which is going to be nn.sequential. We flatten it, because remember, you always have to flatten it. And then we do nn.linear layer. So the in features is going to be the hidden units times 13 times 13. And the output features is going to be the output shape of what we want, of how many classes do we want to define. So before I move forward, I'm going to move forward, I'm going to explain a little bit on this part. So where was it? Da, 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 da. There we go. Where did this in feature shape came from? It's because each layer of our network compresses and changes the image, the shape of our input image to this. So let's try to print this out and see what's happening. So when you get confused on what the shape is going to be, a very good idea is to just test things out. So we're going to do that by just writing a forward function. So forward self x, which is going to be of type torch tensor. And then we're just going to say that we are first passing the data into the first block. Then we print its shape, print x dot shape. Then we pass it to the second block. Then we look at its shape. Then we pass it into the third block, which is the classifier. And then we look at its shape. And then after all of that, we return X. And now to actually run this, we will write model equals to the name of this class. So tiny VGG. And then we can just look at this. Oh, because it's not defined. Wait, let me just run this once. Now, if I write model equals to tiny VGG and we scroll over it, we can look at the doc string that we created, and it says that it requires an input shape. So let's say we have an input shape of 1, the hidden units as 10, because there are 10 classes. Not 10 classes, but and the output shape as the length of the class names. And we have to define device as well. Where is my device? Device. Where is my device? Here it is. So we can add this here, and then we can do. We can do. Where's the forward pass? Forward. Stepping through. Yes. Class names. Dot to device. And then we can write model. And I have an error. Wait. Now that's fixed. Device is not mentioned. And there we go. So, what just happened, right? Basically, what we just did was we created a convolution neural network wait. I think it's F. Nope. It's not F12. Is it control space? Nope. Hover. Why am I not getting my doc string? Control Shift Space. I think I have to do it like this. There we go. So we're creating like a convolution neural network like this, where we have our image size and then we're defining the number of channels. And then we created our first convolution network. Then we applied the ReLU function. Then we created the other convolution block. Then we applied the ReLU. We then did the max pooling. So this is the first convolution block. Then this is the second convolution block that we did. And then we get our output as 10, which is the class that we want. So the input ship 1 over here is basically telling you the number of channels that you want, right? Since we are working with grayscale, that's why we said the number of channel is 1 over here. In the image over here, we have 3 channels, green, red, green, blue. But if we wanted only one channel, which is black and white, then this value would be 1. Moving on, hidden units equals to 10. The second part is an integer indicating the number of hidden units between the layers. Um, this basically means, what does it mean? What does it mean? What does it mean? Says 3. Wait. Hidden unit specifically controls the number of convolution filters. Okay. Um, feature maps kernels. So basically, if I can find a good image, you have an, wait, before I explain this, um, okay, okay. Okay, got it. All right. It's better that I do it on Paint because it's more easier when I do it with my own illustration. So, imagine that you have an image. I can take this image, for example. This is an image of a cup. This is, for example, assuming that this is a 5 by 5 image. You apply a kernel over this. Let's say this is the kernel. And what this does is it detects vertical edges. For example, this thing is called a kernel. And what you do is you basically slide this entire thing pixel by pixel. You apply this operation over this, and your number, so this is like one filter, and then you could have another filter, and what that does is it detects the number of horizontal edges, and then you could have another filter, whatever. These are basically your filters. So you have a kernel, a single filter is called a kernel. And when you have multiple of them, then you're basically calling them as filters. And when you apply this operation on this image, the output image that you get. So for example, if this was a 3 by 3 kernel, and then it had like 10 channels. So right now, this one has only one channel because it's black and white. When I apply this for vertical edges, so I get one image, then I apply it for the other filter, for example, the horizontal edges, then I get another image, then I apply for another filter, I get another image, so on and so forth. So for a single image, I'm applying 10 times the filters. So that basically means the output image that I'm going to get is going to be of some width and some height, and the number of channels is going to be 10 because that's the amount of filters you're applying. And this output image is basically called your feature map. So in our code, input shape is basically defining the number of channels that you have in your input image, which is this thing over here. So that's this thing. The hidden units is basically explaining how many number of channels do you want for your kernel. So you can think of it as the number of filters. And then the output shape, this it comes for the very last layer. So that's for this one that you are basically you're basically classifying, I think 10 classes. So let me quickly review this. Input shape, hidden units, then from the hidden units to the hidden units, and then hidden units to hidden units, and then units to yes, and then hidden units to 13 by 13, and then the out features to your output shape. Yes, that works. So over here, this is basically explaining what we did. So first we started with the first one channel and we applied 10 channels. Like over here, like I explained, you had one channel, I applied 10 channels, so an output of 10 channels is then given. And then I do the same thing again. And then at the very end, I flatten it. So I take the entire image and I convert them into a series of neurons stacked together. And then this is basically 1690, and then I am basically classifying only 10 classes, and that's given by over here. Okay. So the question is, why 13 by 13? Why 13 by 13? Mm-hmm. Okay. By the way, for people who are joining in, just like learning a little bit of AI, you could say in short. So I'm doing a bit of like quick revision right now for myself, and then I'm going to implement a research paper. So right now I'm just like revising how I used to code a little bit. Okay. Mm-hmm, 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 mm-hmm. Okay.
Hey, I mean, if you're in this course,
Mm-hmm.
welcome back.
Okay, so basically an update. I'm trying to understand where did this magical 13 by 13 number came from. So I'm just going to look at that in a little bit detail and then explain how we got that. Okay, so little bit information I trying to understand where is this magic number coming from. Think there is a little bit of understanding where I got this from. Just a second. So I accidentally, where's the comma? Go to your init function and delete that comma. There's a comma. I accidentally put a comma here. That's why. Okay, let's run this again. First compile the model. There we go. So it says matrix 1 and matrix 2 shapes cannot be multiplied. So I got 1 by 160 and then we got 10 by 10. So that should be a cue to understand why we were multiplying this by 13 by 13. Again, just give me 1 to 2 minutes and then I'll come back and explain how I got that 13 by 13. Okay, so um, a little bit of understanding what's happening over here. Um, so when we pass our image from the first convolution, first ReLU, or in short, when we pass it from here to this entire first convolution block, the image gets a little bit smaller. So first it starts with 64 by 64 because this image is of dimension 64 and 64. And when we pass it through the first convolution, it gets reduced to 30 by 30. So for our case, when we are sending an image of 28 by 28, and when we pass it through our first entire convolution block over here, then the image size that we get, so let me just write that down over here, the image size that we get. So the output shape after convolution 1 block, that is this thing, this thing. And I did not add the quotation. And then we can copy this entire print statement. And then we can say that this thing is what we get after the second convolution block. And then we can also do the same thing over here. And that we get this after the classifier block. Classifier block. So our image, it goes from 28 by 28 when we apply all of these steps, convolution, ReLU, and then max pooling. The image gets reduced from 28 by 28 to 12 by 12, and then we do it again for the other convolution block, so this gets converted into 4 by 4. Now the problem is that if we multiply all of this down, because again we are flattening it, if we multiply this, so let me say 10 times 4 by 4, we get a value of 160, right? So you can imagine that when we get this image over here after the second max pooling part, um, this image of having 4 channels. So let me just make this with blue, with 4 channels of dimensions 10 by 10, because we flatten this down into series of single neurons. This gets converted into 400. No, sorry, 160. 160, because it's 4 by 4. Sorry. So I made a mistake over here, made a mistake here and here. So this should be 10. There were 10 channels, and this is an image of 4 by 4. Okay, so we get 160. And then we are basically connecting those 160 to 10 neurons, right? And we need to tell this to our code. So what we did was we passed a random image of the same dimensions that we were like expecting it to do into the model. And the model said, hey, well, we need this dimension. And the dimensions that you gave of me was just this hidden units, right? So what is this hidden units? This hidden units was 10, right? So I told my model, hey, this is 10, but I never told it about this 4 by 4 thing. So in our case, we just have to multiply this by 4 by 4, and then when we run this, it should work, and it should tell us that the output shape of the first convolution block is this, the second is this, and after, when we do it for the classifier, it gets converted into 10. And this basically means that we have successfully implemented the forward function. So that is how we get these magical numbers, as per to say. So that was pretty fun. Why did we do unsqueeze? So basically, over here, this is a random tensor image, and the model is expecting a batch. It's expecting an image of a batch. Um, yeah. So what we do is we add one more dimension to it. So let me just show what I mean. So when we do image, random image tensor, right, and we write its shape, it tells us that this is of shape 1 channel, which is grayscale, and of dimensions 28 by 28. But when I do dot unsqueeze 0 dot shape, now we added this extra dimension. So this is for the batch size, or not the batch size, but the batch number. This is for your number of channels, and then this is your dimensions. So that's why we did the unsqueeze part. And if we don't do that, so it will give you an error. that uh okay, so for now it worked because right now um the input ship was 1, but normally this doesn't works. You have to define your batch number. Okay, so that's good. With that, I think we're basically done, and now we can go modular. Okay, so just gonna take a small break. Gonna look at if there is anything in the chat. Okay. Leo Moss and best viewers on Strebu remove the space. I have no clue what that means. Okay, so it was an advertisement, I think, from a random guy. Yeah, spam advertisement. Okay, so nothing in the chat. All right. Um, let's go modular. Okay, so the model is now there. Now we don't need these print statements anymore because we already know what that was. And now we also know how to create this entire thing, so we don't need this anymore. So the first step was how to get our data set, which is over here. Step 1, creating the data loaders for our data step. Step 2 was creating the model. We created the model. Now the step 3 is to start our training. Step 3, this is not, there we go. Step 3, create training and evaluation loops. The next fun part. So let us do this now. So we're going to do import torch again. We're going to do from tkey do m, auto import tkey do m, from typing import a dictionary, a list, and a tuple. These are some necessary libraries that we want. Then we are going to define our training step. Training step. Uh, I can technically also create the doc chat over here as well, right? Yeah. There we go. That's way better. I can close you. Okay. To be honest, I don't need you. So I'll close you. There we go. Much better. Okay, so the training step. So we're gonna have our model. This is going to be a torch of a data type of torch nn dot module that we just defined earlier. We're going to have a data loader. This is going to be of type torch dot utils dot data dot data loader. How do I know this? Well, I just know it. No, basically when you write your training data loader, which I've already created earlier, like an example of it, it gives you or returns you the type of that object as well. I think you can also write type and that will also work. Yeah. So that's the data loader. Then we have our optimizer. So torch.optim.optimizer. And then we're going to have our device. So this is going to be torch.device. And this is basically going to be it. But this is then going to return us a tuple of float and float. Let us begin. So there's an error here. This should be like that. There we go. Again, docstring. I'm not going to write the entire docstring. Just going to put the docstring here so that you can read. Okay, so first thing, put the model to training. Put the model to train. First, train the model. Model.train. Then we're going to do setup the train loss and the train accuracy values. This is going to be the train loss, comma, training the accuracy. So this is where we are evaluating the model. So this is going to be 0, comma, 0. Then we're going to have loop through the data loader, data batches, and then for the batch, comma, x and y in enumerate data loader. So what we're doing is we're unzipping the data loader, and that's going to return you the batch number and also the x, which is the image, and the y, which is the label. We send the data to the target device. So this is x comma y equals to x dot to device, and then we do the same to y as well. So y dot to device, and then we do one, which is the forward pass, which is y prediction equals to the model of x. Then we do the other one, which is the calculate the accumulated loss. So that is going to be done by having a simple loss function, which is loss underscore function, where we just give our y prediction and our y. So we have to define this function somewhere. Yeah, let's get that in a little while. Once we get our loss, the test loss is going to be plus equals to the loss dot item. Then we calculate and accumulate the accuracy. So this is going to be the test prediction underscore the labels equals to test prediction logits dot arg max of dimension equals to 1. Then we do the test accuracy plus equals to the test prediction labels equals to y dot sum, and then we do dot item. We divide that by the length of the test prediction labels. And then we do adjust the metrics to get the average loss and the accuracy per batch. So we do test loss equals to test loss divided by the length of the data loader. Then we do the test accuracy, which is going to be the test accuracy divided by the length of the data loader. And then we do the return of the test loss and the test accuracy. Then we define our training. So this was the training step. Now in training, again, model torch.nn.module. Then we have the train data loader torch.utils dot data loader. We have the test data loader. Whoops. Test data loader. Oops. Of type. Again, same thing. Utils dot data loader. The optimizer torch dot optim dot optimizer. The loss function torch dot nn dot module. The epochs and the device torch dot device. So this is basically going to return a dictionary of string and a list. That is our function. Then comes our docstring, which is basically saying that you're passing a target Pytorch model through the train step and the test step functions for a number of epochs, training and testing the model, calculates and prints and stores the evaluation metrics. These are all of the parameters you're then returning. So in the form of training loss, training accuracy, whatever. And then we can create our dictionary of this thing. And then we can then do our loop. So loop through training and testing steps for a number of epochs. So we're just saying for epoch in tk_do_m, range of the epochs, train loss. Did I say epochs? Epochs, yes. Train loss, comma, train accuracy is going to be train step. This is where we say model equals to model. Data loader equals to data loader. The training data loader. Then we have our optimizer. So optimizer equals to the optimizer. And then we have our device equals to the device. That's done. Then we do that for the test loss. So this is basically like the validation. You're doing validation over here. And then you do test step, right? Which I forgot to write. So let me write this down again. Define the test step. Oops, test step. So model torch.nn.module train data loader. This is torch.utils. No. No. The data loader, because there's only one data loader over here. that's torch.utils.data.data loader. So what do I want? I want the model, I want a data loader, and then I want the loss function. So the loss function, that is basically torch.nn.module. Then I need my device, which is torch.device. And that's going to return me a tuple of float comma float. Perfect. Then comes the doc string. Okay, so this is just performing the step. For every epoch, we're performing a step where we are basically um, pushing our images to the device. So put it into the GPU. Then what we're doing is we are calculating the loss function. We're calculating the accuracy and it's returning the loss and the accuracy. So you do the training by putting the model into training mode. And now we're going to do it for here. So put the model to inference mode, or sometimes also called the evaluation mode. You're not doing inference, you're evaluating the model. So you say model.eval. So now you're not updating the weights anymore. Test loss, comma, the test accuracy, that is 0 by 0 initially. And now you do the inference and you're now testing what is the test loss. So we turn on the inference context manager. So we say with torch.inference mode, we do loop through the data loader batches, and then we do for batch comma x comma y. Enumerate the data loader. We do x, we send the data to the target device. We do x comma y equals to x dot to device, and then we do y dot to device, right? Then we do the same thing, which is this entire thing, do the forward pass, get the logits. Think so. I confused it a little bit. Sorry. That's why. Sorry. I made a little bit of mistake here. Loss function. So sorry. So model, and then we have a loss function, which is nn torch dot nn dot module capital. So this is correct. This entire thing should belong over here. My bad about that. Just a second. So this should not be called this. This should be called a training loss. So we do the forward pass. We calculate the loss. After the loss, we apply the optimizer. So 3.optimizer 0 grad. So optimizer dot 0 grad. So basically what we do is we set the weights to 0 so that it doesn't have any correlation to the previous batch. So we zero the gradients out. Then we apply the backward. So what we're doing is we're computing the entire derivative. We get the loss, right? Um, and then what we do is once we get the the gradient, right, we add the weight to it, and then we're stepping through to it. So we are doing the optimizer step, which is then the optimizer dot step. So we're updating the weights over here. Okay. Um, so let me just copy the entire evaluation metrics. So ba 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 ba. Similarly here, we do the same things. First, we get the forward pass. Once the forward pass is complete, then we calculate the loss. Once the loss has been calculated, then we calculate the calculate and accumulate the accuracy, and then we're returning this. So now we have both the test step ready and the train step ready. Why do I not have train loss? It should be train loss. Cool. Um, that is the training step. Why is this not green? Why did I make a mistake? Utils dot data loader. There we go. Perfect. Then we have the training part here. So now this is ready. Ready. Um, now we need to create the loss function, right? So the loss function is the loss function, which we are basically passing through. Which should be also defined here. So that's the loss function. Loss function is the loss function, and device is a device. And once we do that, then we can print what's happening, and then we can return the results. So for each epoch, we print what's happening, and then we update the entire results, I think. And then we are returning everything at the end of the epochs. So now we have our entire training part complete. Awesome. So now we can train our model. Now to save our model, so once we have completed the training part, the next step is, so step number 4 is basically saving the model, right? We just don't want to throw the model now, so we are now going to save the model. So from path lib import path, we're going to define a function called save model torch.nn.module. We're going to do the target directory, so that's a string. We're going to have a model name, which is also going to be a string. And then what we're going to do is we're going to define what we're going to do here. which comes into the docstring. Docstring it is. So we first create a target directory, create target directory. The target directory path is basically path and then the target directory path.mkdir. So make a directory, parents equals to true, exist equals to also true, and then create model save path. So we assert model name dot ends with dot pth if that is the case, or if or model name ends with dot pt. So if it's a Pytorch model, then what we want to do is, if it's successful, if it's not successful, then we're basically going to say, hey, it should end with a .pt file or like that. And then what you're going to do is you're going to save. So the model save path is going to be the target directory path slash model name, and then save the model state dictionary. So print. So you're basically saying that you're saving the model to this path, and then you say torch.save object equals to the model.state dictionary, and f equals to, so your writing mode will be to this path. So you give a target directory, you give the model name, and the model name should end with a .pt or .pth. If it doesn't, then it will give you an error and it will not save it. If it is .pt, then you're just going to add the target directory path, add a slash, and then add the model name. So it saves the model over there, and then you're saving the model like this. Okay. And now with that, we are just left with one last step, which is step 5, main code. And then we're basically done. So a quick recap. We started with creating data loaders for our data set. Then we created the model. Then we created a training and evaluation loop. Then we saved the model. And now we are creating the main code, which when you run this, then it runs everything else. So some libraries: import OS, import torch, import data setup. Sorry, this comes afterwards. From torch vision, import transforms. We are setting up the hyperparameters, set up hyperparameters. So the number of epochs is going to be 5. The batch size is going to be 32. Oops, no commas. The hidden units, so this is the number of filters. I'll say number of filters. This is basically 10. The learning rate is 0.01. Then we set up the directories wherever we want to set the directory. We get our device. So set up target device. Then we create our transforms. So create transforms. So data transform is basically transforms.compose, and then this is transforms.resize. So we are resizing our image to 64 by 64, but in this case, I'm not going to apply resize over here. I'm just going to convert it into transforms.tensor. I already have tensors, and I already have my data loaders. So I will skip the data loading part for now, but this comes, so you have your directory, you have your transforms, because I'm already using a data loader for my MNIST, fashion MNIST dataset. WhatsApp number, please, sir. But why do you need my WhatsApp number? For what reason? Okay, so we get our training data. We can also get the training data and that as well. So we can also get the test data over here, which is going to be similar. Uh, the test. Thank you for the like. The test data set is going to be fashion MNIST data set. It's going to be data test to true. Oh, sorry. If we just set this train to false, this automatically means that we're talking about the testing data set. We already have the so this is getting the test data set, so it's still true. Transform.tensor equals to none. Okay, let me remove my data. Poof. Why did it not poof? Because I'm not over there. And poof. There it goes. Okay, so we're downloading the data set. Once the data set is downloaded, then we create our data loaders. Create data loaders. So the data loaders, again, we are not going to be using this data loaders because this was for custom data set. We're just going to go for the very simple data loader, which was this one. Very simple. And then we have the similarly for the test data loader as well. Data loader test data, comma, batch size equals to the capital batch size, comma, shuffle equals to true. Test data loader. Or we can set this to false because we don't want to shuffle the data set. Okay, let us begin. And continue. Let's continue. So data loaders are here. Let's create our model. So create model, right? And the model is just going to be tiny VGG model that we created earlier. So that's over here. Then what we do is we give in the values. So we know that this is a black and white image, so we give an input shape of 1. Let's put it in the other line so it's more cleaner. So it's a black and white image. The hidden units, which is the number of filters, that's over here. And what does it need? It needs an input shape, which is the number of input channels, the hidden units, which is basically the amount of filters, and the output shape is the amount of what? The classes that uh, we want to predict. So that is going to be, so output shape is going to be the length of the class names. Have I defined the and then we are going to do this or push this to device. So we're pushing it to GPU. We haven't defined the classes, right? The class names. Uh, yes, this should be done over here. Class names equals to the length of the training data loader. Okay, I think over here we were defining it like this, and we did not return that class names. That's good. Test data would now work. Uh, training data, test data, training. What did I miss? What did I miss? What did I miss? I missed something, something, something. So training data, testing data. That's what I missed. My bad. Okay. So to get the class names, I have to grab an image and then I can get the class names like we did over here. Right? And to get the class names, we can just get this train data dot classes, and then just do the length of that. That will give us the class names. Perfect. No, that will give you the classes and the length. Now it's correct. Okay, model has been built. So now the model has been built. Now what we're going to do is now we're going to create our loss function. Set the loss function, set the loss function and the optimizer. Very simple. So the loss function is just going to be cross entropy that we're going to be using, cross entropy loss. And the optimizer that we're going to be using is going to be Adam. Torch dot utils dot Adam, not here. Sorry, torch dot optim dot Adam, and then we're going to set our model dot parameters, and we are going to set this to our learning rate, and then we are basically going to train our model. So just call train model equals to model training data loader equals to the training data loader that we just got over there. Now we just have to fill these values. The test data loader is going to be the test data loader. The optimizer is going to be the optimizer. The loss function is going to be the loss function. The epochs is going to be the number of epochs. Then we have what remaining? The device is going to be the device. So that will do the training. And once the training has been done, we want to save the model with the help. We want to save the model. So this will be save model, model equals to the model name or target directory can be models. And the model name is going to be our first model on stream .pt .pt. And with that, when we run this, I do not know why I'm getting this thing. I should have gotten a proper tkdum. Not sure why. Maybe I have to restart this. Hmm. Maybe I didn't install this IP widgets. Oh no, this is I think first downloading the dataset. Train is not defined. But before that, let me do pip install ipy widgets. Train is not defined. Why not? Because I didn't run this node or code. We can delete this. We don't need. Then we can run this as well. And then we can also run this one. And then we can first save this file, close this, and then open VS Code again. VS Code. Okay, let's take a look at chat. Probably nothing that we have right now. Yep, we don't have anyone. That's fine. That is perfectly fine. Nothing. Nothing on Twitch as well. Good. So we're just going to wait for this. For some reason, it's taking some time. I don't know why. This might take some time to load. So we're going to wait. Wait. And after waiting, then maybe we will see something good. Do I have Jupyter installed over here? Let me check. Jupiter. I did not install Jupiter. That is why it didn't work. Tell me why it ain't nothing but a heartache. Bow, 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 bow. Do, 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 do. Let me restart. Where is run all? Should be run all somewhere. Mm, there we go. Run everything. Is it downloading properly now? I think it already downloaded, so it's not showing me anything over there. Um, and it failed. Okay, so the TQDM now works. Perfect. But there is one thing missing, and it says um training loss, training stepped, missed one thing. Okay. Um, so we have the data loss function equals to the loss function. Okay, let's run this again. New error. What? Do I not have? I have my loss function here and here and there and there and there. So this is correct. That is correct. And then I think this is not used. Optimizer. Why is this not used? Because I didn't add a comma. Amazing. Most stupidest mistake ever. I didn't add a comma. Let's try and see if it works now. Okay. And the training begins. And now we wait for the model to get trained. So for each of the epochs, we're getting the loss, we're getting the accuracy, the training loss, the training accuracy, the test loss, and the test accuracy. And then we can save our model, which is over here. Awesome. So let's take a look at the inference, because we want to do inference to actually see that whatever we did, does it even works? at all or not. Um, so to load the model, it's fairly very easy. So you say load model equals to, again, tiny VGG. The input shape equals to 1. You have to make sure that this is same. So the hidden units equals to the number of filters, and the output output shape is basically the length of the class names. And that after that, um, we push this to our, you know what, I'm going to make a function out of this because it's really annoying. Let me create a new step. Step 5, load model for inference. We're going to rename this step 6. And we are going to define load model. Okay, so what do we want? We want all of this data. So we want an input shape, which is going to be of type integer. We want the hidden units, it's going to be of type integer. We're going to need the output shape, which is going to be of type integer again. Then we need the model, which is going to be torch.nn.module. We are going to need our data loader. So the data loader, this is going to be torch.utils.data.data loader. Then we need our um, we're already getting this. I want inference. How do I get the inference? Okay, so for inference, we do require the model. We do not require all of this. We just need the model. We need the image, or we can say the data for now, which will be of type this thing. So train data dot type of the train data, but that's that. No, of 0. It's a tuple. So the data will be of type tuple. So import torch, import from typing import tuple. So we have our tuple here. We have our model. Why There we go. So we have our tuple, we have our module. We do not require the data loader, and I think that's pretty much it. Uh, um, I think so. I could be wrong, but I think that's pretty much it. And we're not going to return anything because I'm just calling it and then getting my results. So let's start the the inference code. So we get the image, we get the label, and we get it from the data that was just received to us. So we open that up. Then um, we are now sending this data to our model, which we just trained. So we do um, image for model is going to be image dot unsqueeze 0 because our model expects a batch, and then we do this to the device. So we also need to give device as well. Device is going to be, I think it's a string. It's a torch dot device. Sorry, it's a torch dot device. Then, so we're preparing the image for the model. We are um, extracting the image and label from the data. So that's one. Then in the third thing we're doing is performing inference. So perform inference. And then we do image for the model. Sorry, model.evaluate eval with torch.inference mode. And then we're calling this entire thing again, which we have already done in the test step, which is this thing. Um, and then over here, we're going to get predict the logits equals to the model, and then we are basically sending the image. Prediction probabilities equals to torch.softmax, and then we do the prediction of the logits. Dimension equals to 1. This part of the code is the classifier that we mentioned. I think. Okay. So logits into probability, and then probability to the label. So this will be prediction label equals to dot argmax, and then the prediction probabilities to 1. That's probabilities plural, and then your prediction, okay, name, which is 4. And then we